Let's return to this idea of a two-port device as a source transformer. So we have an original source, and then we've connected a two-port device to its output. And of course, we can collect the whole circuit together and replace that with its Thevenin's equivalent. And again, we thought of that as a two-port device as a source transformer in that case, that the output voltage after transformation is very much different than the original voltage source, and likewise the output impedance is very much different than the original output impedance ZG. And here were the transformation equations, and you can see that those values, generally speaking, are very different, and they depend on the transimpedance parameters of that two-port device that are doing the transformation. Again, V out is very different than VG, and Z out is very different than ZG, generally speaking. There is one more parameter, though, of a source that we have not yet discussed with respect to transformations, and that is the available power of the source. Remember, the available power is a source parameter. It is independent of what is attached to it. Delivered power of a source is not a device parameter because it depends on the source and on what's attached to it. The available power is independent of what's attached to it. It is a value that is constant with respect to that source or the load connected to it, or if in fact any load is connected to it. And so we ask ourselves the question, what is the available power of this transform source? What is the relationship between the original available power and the transformed available power? You will recall that the available power of a source can be determined with this expression. It's simply the magnitude squared of the source voltage divided by 8 times the real part of the source impedance, or the resistive component of the source impedance. And since these parameters depend only on the source themselves, again, the available power is a source parameter. We don't need to know what's connected to it. It's the same value regardless of what is connected to it. The available power is independent of the load. Now we have a transform source where we have V out and Z out, and of course we could simply go through and calculate the available power now of this new transform source once we know V out and Z out, and it would be of similar form, the magnitude squared of V out divided by 8 times the resistive component of that output impedance Z out. And so we could calculate these and compare them, and we might be interested, since these are real values, to see, are they equal to each other? Is one greater than the other, or is the other less than the other? Under what conditions would there be a difference? And it turns out we could calculate them under different values or different two-port devices, but what we find is that the results are dependent on the characteristic of those two-port device, specifically the characteristics that we've talked about just now. Whether that two-port device is an active device, a passive device, lossless device rather, or if it is a lossy device. If we have a lossy two-port device, a lossy two-port network, then we find and we can show that the available power of the transform source will be less than the available power of the original source. And to a certain extent, this is no surprise. If we have a device that will reduce the rate of energy flow through it, then it's reasonable to expect that the device likewise would reduce the rate of maximum energy flow. And that maximum energy flow, of course, is the available power of the original source. So a lossy device will reduce the available power of the original source that, it transforms. Alternatively, if we have an active device, an amplifier, we know that that two-port network can increase the rate of energy flow through it, and so it's not unreasonable to expect, and this is the case, that a two-port device will transform an active two-port device will transform a source into a new source whose available power is greater than the original source. The two-port device can increase the available power of the source. This is one way of thinking of an amplifier. By how much does it increase the available power of a source that it is attached to? And that's one way, it turns out, of specifying the gain of an amplifier. So If a lossy device will decrease the available power of a source, and a active device like an amplifier will increase the available power of a source that it transforms, you can kind of see what's going to happen then to a lossless device. Will a lossless two-port device leave the available power of the source unaltered? Let's see if we can determine whether that's true. Recall, if we have a lossless two-port device, then the impedance matrix is a reciprocal matrix whose elements are purely imaginary. The real component of each element is equal to 0. And so it'll be of this form. We know that the transformed source voltage Vout has a form such when we insert the transimpedance parameters, then would have this result. Likewise, for the output impedance of the transformed source, if we insert these purely imaginary transimpedance parameters, dual algebra, it would give us this result here. So this is the transformed output voltage and output impedance for a source that's been transformed by a lossless two-port network. Now we're hoping to determine what is the available power of this transformed source, and to determine that we need to take our output result and determine its magnitude squared. And so with a little complex algebra we get this result. Moreover, we need to determine the real part of Z out. And so what we find there, remember x21 is a real value, so really all we have to do is find the real part of the conjugate of Zg, and of course that is just Rg, the resistive component of the original source impedance. And so this becomes then our result. From these two values we can determine the available power of the transformed source, a source that's transformed by a lossless two-port device. So then we take the previous results and we insert them into the available power of our transformed source, magnitude squared of V out and R out. We insert them in there, we get this ugly result, but fortunately there are things that cancel out. The numerator and denominator have terms that cancel each other. And likewise, well, when we reduce it all the way down, we get this simple result. We look at this and we think, gosh, we've seen this before. The magnitude squared of Eg, the original source voltage, divided times 8 times Rg, again, the original source resistance. And of course, this term is exactly the available power of the original source. And so we find that the value of the transformed source, the available power rather, of the transformed source is precisely equal to the available power of our original source. If we connect a lossless two-port device to a source, even though we will change dramatically perhaps the source voltage Vg into some different value V out, and we'll change dramatically perhaps the source impedance from the original value of Zg into a new value Z out, what we don't transform is the available power of that source if the two-port device is lossless. So the available power of the transform source is equal to the available power of the original source, again, if that two-port device is lossless. So this result can cause some confusion, because if we look at the transformed resistance, output resistance, R out and compared to Rg, we see that we could come up with a two-port device where R out is greatly decreased from the value of Rg. This value may be something that is much less than 1. And of course, if we did that, we might harken back to our ideal source impedance analysis, where we said if we want to make the available power of our source larger, what we want is a source whose output impedance is ideally reactive, at very least make the resistive part of the output impedance as low as possible. And this appears that with a two-port device, we can transform the output impedance from one with a fairly significant source resistance into one that perhaps has a very small source resistance. If we did that, it seems like it would increase then the available power of our source. Isn't this a way of changing our source impedance such that our available power can be increased? But it turns out there's a catch. So the catch is that our two-port device, even though it does alter the source impedance from RG to ZG, RG to R out rather, it also alters the voltage source from a value of VG to a value of V out. They're coupled together. And this, I referred to this a little bit when I talked about this idea of setting the optimal source impedance, where we say, oh, I want to set the source impedance such that the resistive part is as low as possible. Well, that was for an optimization where VG was constant. If I could just go in and alter the source impedance while leaving the voltage source the same. Again, that's an academic problem, really. It's very difficult to do, and like we've shown just shown here, we can alter the source impedance with a two-port device, but we always simultaneously alter the source voltage as well. And if that two-port device is lossless, as we've just shown, we find that they both are coupled together in a way such that the available power is preserved. With a lossless two-port device, I can change V out, or VG to V out, and ZG to Z out, but I cannot alter the available power. It's the same both before and after the transformation. And so even though Z out may have a much smaller RG, or R out, let's say, could have a much smaller value, it turns out because the magnitude squared of V out will have a proportionally smaller value such that the available power remains the same. Let's do an example to show that. Let's say we start out with the source and we attach a lossless two-port device in front of it. And of course, therefore, we've transformed the source voltage into a new source voltage and the source impedance into a new source impedance. Let's say for this example, the the resistive part of the original source impedance is transformed to a value that is 4 times larger than its original. So R out is now 4 times RG. We might expect that the available power of this transformed source, therefore, to decrease by a factor of 4. After all, the source resistance has increased by a value of 4. But what we'd find in that case, if the two-port device is lossless, is that the magnitude squared of the resulting transformed voltage source is likewise 4 times larger than the original. In our available power, the numerator is proportional to the magnitude squared of the voltage source. The denominator is proportional to the real part of the impedance. And so if both of these change together, then the available power will be invariant. And so for a lossless device, again, we could go through and increase the source resistance by a factor of 4, but what we'd find is that the magnitude squared of the transformed voltage source would likewise increase by a factor of 4, canceling each other out, and we would get exactly the same available power. This would likewise be true if we did a transformation that dramatically reduced the output resistance. Let's say the output resistance after the transformation is just 1/10 of its original. That seems like good news. That's what we want. We want our output resistances to be as small as possible, to be output impedances to be as reactive as possible. But in that case, we would find that our voltage source magnitude squared, would also reduce by a factor of 10, and therefore the available power would not increase at all. And so again, I want to show or try to point out that this idea of somehow going in and messing with the source impedance while leaving the source voltage unchanged is very difficult. Remember, these are not a physical definition of the circuit. This is an equivalent circuit that we have here. If we want to go through and ultimately increase the available power of a two-port device, we either have to redesign the two-port device itself, or if we want to attach something to it to transform it into something with a higher available power, that two-port device must be an active two-port device. That two-port device needs to be an amplifier. And that's the way ultimately we do try to increase the available power of a source. If it's not sufficient, we attach an amplifier.